Welcome everyone. Our session today is about keeping LLM performance in check, how we can monitor, detect, and automate responses to make our AI systems remain reliable, cost efficient, and trustworthy in real world use. I'm Mohammed Abed. I work as information security analyst at Splunk Cisco.
Hi everyone, I'm Priyanka Rallabhandi. I'm an information security analyst at Splunk. I'll walk you through how we approach implementing monitoring of LLM applications using Splunk Observability Cloud, ITSI, and SOAR. Every company wants to use LLMs because they promise efficiency, automation, and innovation at scale. But they don't always behave like we want them to be. Going rogue means LLMs might introduce high latency, taking more time to run the responses, to generate the responses, hallucinate facts, giving wrong answers which might lose trust, cause token explosions, making the costs very high. That is why it is very critical to monitor LLM behavior like we would monitor any high-risk systems. Our approach is to monitor, detect, and automate. We are monitoring metrics and traces with Splunk Observability Cloud, detecting anomalies using ITSI, and automating remediation with Splunk SOAR. Let us now break this down step by step. Our solution is to instrument LangChain-based LLM app. We capture the key metrics and then forward the data to Splunk Observability Cloud. Before I directly go to the flow, I'll talk about few terms which I'll be speaking about in this session. LLMs are large language models which are trained on large amount of text. They usually respond in human-readable text. LangChain is a framework in which we can develop LLM applications. Olama is a model which we are using in our demo. OpenTelemetry is a framework which is used to onboard traces, metrics, and logs. This is a vendor-agnostic framework to onboard the telemetry. Traces, metrics, and logs are the backbone of observability, which is used for real-time monitoring. Splunk Observability Cloud, ITSI, and SOAR are Splunk products which we have used in our demo in this session. LLMs are trained on billions of text documents. They learn patterns in language and not in facts. They use probability to generate the next word or token in a sentence. And now, what are the few limitations of them? Latency is the time taken between request and the response. If there is high latency, the user experience is really low. Token limits, which mean that the LLM can only process a few thousand words at once, and the response is not complete. Coming to cost, cloud-based LLMs can be very expensive without observability. And coming to hallucination, the LLMs might generate responses which are fake and not complete correct answers. That is why we want to monitor them. And why does it even matter to monitor LLMs and their related apps? Without instrumentation, LLMs are black boxes. We know that we are getting the request and response, but we don't know what is exactly happening in them. Not just monitoring the LLM apps and their metrics, it is also very important to monitor the infrastructure on which these LLMs are hosted. This is a very beautiful picture which shows us how it looks like without observability and with observability. This is a complete black box without observability. But when we implement OpenTelemetry to our LLM application, we can see that the traces and the dashboards are clearly visible like a glass box. Now, how do we monitor the LLMs and their related apps? Meet our app, the LLM Employee LangChain LLM app. With OpenTelemetry, we gain full transparency into how long LLMs take to respond. And what tools are we calling inside our applications? Which steps are causing the delay or failure? we get the entire transparency of these steps using OpenTelemetry. Now, I'm going to show you the flow of our application. When a user queries the application, the LangChain, where we have used the framework LangChain, it calls the LLM, which in turn generates the response. When the entire workflow is happening from user querying to generating the response, we are also using OpenTelemetry in our LangChain app to generate metrics and traces and then sending them to Splunk Observability Cloud or Splunk Cloud or a Splunk Enterprise. LangChain LLM app with OpenTelemetry. Using the LangChain standard invoke method, we are calling a HTTP request to Ollama server, which runs the model Llama 2 in our demo, and the response is then processed. This entire method is wrapped in the OpenTelemetry SDKs, and we can get the metrics and traces from them. LangChain is not just to make an API call or to form a request. It can also be used for very complex use cases like RAG-based question answering from PDFs or internal wikis, which means that when we give a policy document, it generates response using the context of the policy documents from the LLM. We can also create LLM agents that perform actions like code execution and making API calls. You can also use it to create automated reports generation using internal data and multi-step reasoning chains for summarization, translation, and analysis. Let us talk about OpenTelemetry. It is a vendor-agnostic toolkit which is used to generate the telemetry data and send traces, metrics, and logs to any system. We have used Splunk Observability Cloud in our monitoring here. Now, instrumenting with OpenTelemetry. The tracer provider and metric provider allow us to generate the traces and metrics, while configuring OTLP exporters tell us where the data should go to. The batch spanner and periodic exporting metric reader send the data reliably. This is our OpenTelemetry setup in the code. We initialize the tracer and meter providers. We create and configure exporters, which tell us where the data should go to. And we register the exporters with processors to send the data reliably. We start using the tracer and metrics meter, and from now on, the traces are generated. Here are some of the metrics which we are capturing. The Ollama request total is the number of requests which we are making or which we are calling the LLM. The Ollama request duration seconds, which is the time taken to generate the response. The Ollama tokens total, which is the number of tokens we are using in a particular request, in a single request. And system parameters like CPU usage, memory usage. And now, coming to the most important part, pushing metrics to Splunk Observability Cloud. The traces and metrics generated in our app are sent via OTLP HTTP protocol to the OpenTelemetry collector first, which then, using the hotelconfig.yaml, identifies where these metrics are to be sent to. We have given the configuration in the exporters, and on basis of that, we will send the data to Splunk Observability Cloud using the SignalFX exporter. In Splunk Observability Cloud, we can see a comprehensive view of real-time metrics, allowing us to visualize and monitor key performance indicators of our LLM application. Now that we understood how we implemented the onboarding of traces and metrics to Splunk Observability Cloud, let us look at the dashboards which we have built. When we look at it, we have different charts for request duration, system CPU usage metrics, and system memory usage. Here, spikes can easily be identified, and we can set up alerts. When we go to traces monitoring, if we open a single trace, and we can actually understand what functions are being called and how much an API call to make a request to LLM took. Here, we can see the traces in red, which shows that there are some errors in our API calls. We have created some detectors for the tokens, and we can take a respective action on it. We can give a runbook and also add a recipient using an email, or you can even send an alert to Splunk platform like ITSI. We will now see a demo on how we implemented the entire use case of sending the metrics and traces to Splunk Observability Cloud into action. In this demo, we are showcasing how to monitor, detect and act on abnormal behavior in LLM-based applications, specifically high token usage and long response durations, which directly drive inference costs and impact user experience. When we run our app, it configures OpenTelemetry exporters to send traces and metrics over HTTP on port 4318 to our local hotel collector. The telemetry and Olama client are initialized. The app begins sending the prompt and we can see a success response from the LLM. There are also few metrics generated in the logs. Let us go through our hotelconfig.yaml file which the collector uses to receive, process and export the data. Receivers define how telemetry enters the collector. The receiver listens on port 4318 and ingests the data. The processors filter and enrich the data while the exporters send the data to different backends. Here we have defined two exporters to route the data. First, the OTLP HTTP exporter to send metrics and traces to Splunk Observability Cloud using different endpoints and includes the required token for authentication. Second, the Splunk HEC exporter, which pushes metric data via HEC to Splunk ITSI, tagging the data with source and index. The pipelines define how the data flows through the collector. We will now bring the data to life using Splunk Observability Cloud. Here we have two different apps calling their own LLM providers. Our LangChain Olama app is calling the Olama model, while the other LangChain RAG app is calling the OpenRouter API, which is a cloud-based LLM provider. When I open the traces for LangChain Olama app and go to the root trace process request, we see different spans inside the root trace. The spans show us the steps from sending the request to generating the response in the LLM. We are also capturing key attributes like completion tokens, request duration, the model name, prompt tokens and response length in the tags section. I will open the trace of LangChain RAG app and show you the smaller spans inside it. Here, the document retrieval was very quick while LLM generation took most of the time because we called the OpenRouter API. This breakdown tells us exactly where the time was spent in serving the request and we can easily identify performance bottlenecks. We have created few dashboards to monitor the health and performance of our LLM application in real time. We specifically focus on token count and latency since these directly impact both user experience and costs. We have also captured few system metrics in the dashboard. This is another dashboard for the RAG application. It has request response length and also RAG context length chart in the dashboard. We will now create a detector to identify high token counts from our application. Let's give the metric name and then choose from a list of conditions here. For now, we will go with the static threshold, give a runbook URL and then add email as a recipient and also Splunk platform to send our alerts from Oli to ITSI. I'll proceed activating the alert rule and now the detector is set. So whenever the tokens are above 900, we will be alerted and we can keep a check on the number of tokens being generated by the application.
Thank you, Priyanka. So every organization wants to monitor their applications which are using LLM and faster incident detection and response. Manual triage can slow down the mean time to resolve. Our solution to come up with this challenge is using Splunk ITSI to detect anomalies using AI-based thresholds and automate responses using Splunk SOAR. In ITSI, we can create services to monitor the business critical applications. This service can have dependent services which can monitor the application usage, infrastructure usage, and other metrics. Each service is being monitored through several KPIs that reflect the performance, availability, and error rates. Here you can see on my screen, a service tree has been created for my LLM Conf demo service with dependent services. This represents the color. The green represents that the service health score looks good, and when it turns bad, it will turn into the red color. Let's talk about KPIs. So KPIs, you can have several KPIs created for each service. KPI ensures that we track the right metrics for a service health. These KPIs form the basis of both health score calculation and anomaly detection. Each KPI is configured with a real-time search in ITSI running on a scheduled basis. So KPIs are created on the useful metrics for each service so that we monitor what really matters to us. We create KPIs and set up threshold to detect anomalies. On my screen, if you see, when I click on the dependent services, I can see the app user service metrics health score, which is stored as 100, which service health score looks good, and the KPIs which are created in this service. Let's talk about thresholding the KPIs. Instead of setting up the threshold manually, let us allow the system to detect the unknowns and the anomalies. So we utilized a Splunk AI recommended thresholding instead of setting up the thresholds manually. This helps us minimize the false positives and give early indicators when the metrics deviate from the normal behavior. So you can use recommended thresholding configuration powered by Splunk AI, which will be setting up thresholds for you as per the historical data analysis. You can load recommendations and the AI thresholding will be visible on your screen. Now, let's talk about the episode correlation. So instead of sending soil alerts, ITSI groups the alerts anomalies into an episode. And this episode will be helpful for the analyst to validate what is the issue happening on the LLM, on the service which is getting impacted by this episode. So you can view the episodes from alerts and episodes tab. You can filter out the service to view the episodes which have been triggered for the specific service. Anomaly detection is powered by both static thresholds and adaptive thresholds in Splunk ITSI. With a combination of AI-driven thresholds, historical baselines, and aggregated episodes. With the help of the anomaly detection, we are able to detect and respond to issues proactively even before users are impacted. Let's talk about the aggregation policies in ITSI. We can set up multiple aggregation policies to manage events and alerts that are coming from KPIs. Policies define how notable events are created. We can use filters to include only critical anomalies in our aggregation policies. We can have time policies, time windows, and suppression rules in place to help reduce alert noise. We can also configure the episode titles to provide human readable context. You can create notable event aggregation policies to generate actions for the episode triggered by the detection. You can define the filtering criteria and instructions, and then you can provide action rules for the actions to be taken to perform when the episode is triggered. As we are configuring sending the episode event to SOAR, so this is one of the aggregation policies. You can set up an action rule and send the episode to SOAR. So when you're selecting an action sent to SOAR, you need to add up the SOAR instance. Select the SOAR instance where you want to send the episode to with a label. Remember, this label is very important as the playbook which will be executed in Splunk SOAR is based on this label. So this gives us an automated intelligent monitoring system that scales with our environment. So as a whole, we have kept the LLM performance monitoring in check, and we have detected anomalies wherever our application is breaching the thresholds, and we are sending it to SOAR. So to take up this in action, let me go through the demo for ITSI. Hi everyone, I'll be presenting the demo on how we can detect anomalies using ITSI to monitor the LLM application metrics. Let's begin with the service definition. We have modeled our key business service LLM conf demo. This includes dependent services like app usage metrics, infrastructure, Kubernetes pods. These dependent services are being monitored through KPIs that reflect performance, availability, and error rates. As we talked about the dependent services, let's deep dive into one of the dependent services, app usage metrics, which defines application usage metrics on the LLM application. For this service, we have created several KPIs such as duration metrics, failure count metrics, request count metrics, token usage metrics. Each KPI is configured with a real-time search query which runs in ITSI on a scheduled basis. These KPIs form the basis for both health score calculation and anomaly detection. As we have created the KPIs, let's talk about thresholding. Instead of setting up threshold manually, we have utilized Splunk AI recommended thresholding. This will help us minimize false positives and give early indicators when metrics deviate from normal behavior. Let me show you how the system suggests thresholds for a KPI like token usage metrics over the past 30 days. When I load recommendation here, Splunk AI recommended thresholding will work on the historical data analysis and provide me the aggregate threshold values. You can also enable time policies on the thresholding. We have also enabled triggering a notable event for KPI severity changes from normal, medium, high to critical. As we have done with the thresholding, let's talk about the aggregation policies. We have set up multiple aggregation policies to manage events and alerts coming from ITSI. Policies define how notable events are created. We use filters to include only critical components. Here's an example where any KPI in application usage metrics service breach thresholds, ITSI groups them into episode and perform the action as defined in the action rule. So here you can see the filtering criteria and intersections where we have defined this criteria as when the severity is critical and the service name is app usage metrics or high app usage metrics, then it will be performing the action rules which are defined here. As of now, we have selected the action to send an email to the LLM application owner if there is any threshold breach, and we have also selected the option to send to SOAR so that the episode will be sent to SOAR to perform remediation actions based on the playbooks. We have configured the SOAR instance here and we have set up a label. Notice that this label is important as the playbook which you have defined in SOAR will run on the basis of this label. Now let's talk about the KPI analysis for anomaly detection. So ITSI has a feature where you can do a KPI analysis to first check its compatibility with ITSI's anomaly detection algorithms. As you can see, I can run this on the historical data and analyze the KPI data. This uses trending anomaly detection algorithm, and with a combination of AI-driven thresholds, historical baselines, and aggregate episodes, we'll be able to detect and respond to issues proactively even before users are impacted. Here you can see a graph is visible here which has plotted no detected anomalies. As of now, we don't have any detected anomalies. If there are any, it will be plotted out with a red color. Now let's shift to SOAR. SOAR stands for Security, Orchestration, Automation, and Response. It's an automation engine that connects with our IT, security, and business tools. Where ITSI detects and correlates, SOAR executes actions, whether it's collecting evidence, sending notification, or fixing the problem. So SOAR provides us three main benefits: faster response, shrinking MTTR from hours to minutes, reduce risk by containing the threats and outages before they spread, and efficiency, freeing humans from performing the repetitive tasks and allowing a playbook to execute those tasks. We can enable automation by sending ITSI episode events to Splunk SOAR, where playbooks are triggered based on the event content. We can take a look at the flow defining the episode flowing from Splunk ITSI to Splunk SOAR. Splunk ITSI detects the service impacting anomalies and generates episodes. We will have Splunk app for SOAR export installed on the ITSI to send the events or episodes to SOAR. Episodes or episode payload is sent to SOAR using the HTTP request SOAR API. And Splunk SOAR receives the events and triggered the map playbooks, which is run based on the label which you are defining when sending an episode to SOAR. So when ITSI detects unusual behavior like sudden token spikes or suspicious queries, an episode is generated from Splunk ITSI to SOAR. So you can have cost controls in LLMs as a use case, and you can have security event handling as a use case. So when a user is exceeding defined token threshold, ITSI will send an episode to SOAR, and the playbook which will run to avoid this user to make use of high token usage and limit the user usage for the tokens. And like another example is you can have the user who is searching for long prompts and malicious prompts in his query. So you can have that detected using the playbooks. So when such patterns are detected, the ITSA will trigger an episode with the user name, user ID, or metrics, context, and timestamps. And SOAR receives the event and respective playbook is run. So SOAR performs a secure post call to the LLM application and or the similar endpoint, passing the user ID to temporarily block or rate limit the user to prevent further token abuse or model misuse. So this can be very helpful so that before the human taking the action or the LLM application taking the action on the user, we can limit the user with the usage of tokens by running a playbook automating this flow. Remember, as a note, this automation will require strategic alignment with the LLM application teams, as provisioning a control disabled endpoint must be, thoughtful, customized to align with the specific requirement of this use case. I would like to thank you all for learning from our session and giving us time. I would wish you have a great day, and I would request you to connect with us on the LinkedIn profiles, and also you can contact our email IDs if you want get connected to learn more about this use case.